So, welcome everybody. Thank you for joining us today. My name is Laura Denale from Euronovia, and we are a consulting company leading the communication and dissemination activities for the SCORE Horizon 2020 project. The webinar is the 7th episode in the SCORE webinar series, and it is dedicated to presenting the SCORE early warning system and the digital twin approach to tackle climate change. This webinar is led by our project partners at MBI. It's a private company based in Italy, and they will present what is a digital twin, why it has been adopted in our project, how the system is structured. And our colleague from University College Dublin will also run a mini demo to show the graphical interface and how to set up a simulation. So here is the agenda for today. Just a few practical information before we start. The webinar is being recorded and it will be made available in the next days in the SCORE YouTube channel. Also, due to the tight schedule, we are not taking questions after each presentation, but you can ask your questions in the Q&A tab at any time during the meeting, and we will answer them during the Q&A session at the end of the webinar. So, okay, it's time to start, and without delay, I give the floor to our first speaker, Giovanni Serafino.
Thank you very much. Good morning, everyone. I'm Giovanni Serafino from MBI, a company that is leading Work Package 8 in the SCORE project. Work Package 8 is focused on the design, development, deployment, and assessment of a digital twin system with early warning capabilities. This presentation will be held by me as well as by Andrea Rucci, my colleague in MBI, and José Pablo Gómez Barrón from University College of Dublin. This is the outline of the presentation. First, I will introduce you what is a digital twin. Then we will go to explaining the architecture of the SCORE digital twin and early warning support system, explaining also what are ecosystem-based adaptation solutions, so which are the main sub-modules of the system. And at the end, we will make some example of system usage, showing, making a tour of the graphical user interface and showing some practical examples of simulation outputs. So let's start with what is a digital twin. When we want to study a real system and the related processes, we have mainly two possible approaches. One is dealing directly with the real system, which has, let's say, the huge advantage of having the possibility of interacting with the real system. But sometimes this is not the best way to proceed because maybe we have not the system, your direct contact with the real system, or maybe the process we have to trigger can alter or even destroy the system itself. So another way to proceed is creating a representation of the system, maybe a virtual replica of the same system. So we create a digital twin that allows an analysis of the represented system without directly interacting with the real system. Of course, the digital twin of a physical entity needs information on its physical twin. That is, there must be some data collected on the real system, and there should be an information process exchange between the two, the replica and the real system. Of course, to do this, we need models that are important to describe the real system because they tell us how the system is expected to behave. So they are important to make predictions. And on the other hand, we need data that are important since they give us a hint of what is really going on, and they are fundamental for monitoring. So in other words, a digital twin is a digital representation of a real-world physical system, and it is used for practical purposes such as simulation, testing, monitoring, and maintenance. So virtually any real-world object or process can be represented as a digital twin, provided that we have the right models and we have enough data to describe it. In the SCORE project, we are developing a digital twin early warning support system that will assist coastal cities governance in developing collaborative climate resilience management strategies. It will also allow evaluating ecosystem-based adaptation solutions and support in disaster prevention initiatives. And it will be fed with data coming from cities and with hydrological and sea state models, weather forecasts, and also, of course, data from sensors. So without any further ado, let's go to the core of this presentation, that is the description of the architecture of the developed digital twin system. So the digital twin system is composed by several subsystems. The first is the user scenario evaluation. The user scenario evaluation subsystem allows users to simulate extreme weather and hydraulic situations. It will assist in the prediction of the impact of these simulated events on the study area and supports in the assessment of possible countermeasures to these events. Another important subsystem is the early warning support that is devoted to continuous real-time monitoring of the hydraulic state in the study area. It simulates in a very short time the evolution of the hydraulic state in the coming hours, thanks to artificial intelligence machine learning methods, and thanks by the collection of data from sensors and from weather forecasts. Of course, it can raise alerts in case of imminent flood risk. Of course, this system is also equipped with a database that is the container of all the data employed by the system in its simulation and which temporarily stores the system output data. As already mentioned, this system is intended to collect data from weather forecasts and from sensors, so it will have the possibility to interface with weather forecast services, with sensor networks, and if needed, with external repositories. This can be done thanks to on-purpose developed application programming interfaces. These application programming interfaces are something that in general allows a software running on a given system to interact with another software process running on another system. So in this specific case, they will be employed to collect data from the weather forecasts, to interface with the sensor network and obtain the data streams, to exchange data with the eventual external repositories, and to connect the system with its front end. The front end is a graphical user interface that will allow users to operate on the system in a simple and intuitive way. It will also allow setting up and launching simulations with the use module and the visualization of the outputs of both the use and the early warning support subsystems. So let's focus more on the user scenario evaluation module, going to describe its structure. This subsystem is devoted to the simulation of user-defined scenarios. So it includes some models, in particular sea state models and hydraulic models, that describe, let's say, the underlying physics when an intense rain rate or river discharge event occur. And thanks to the GUI, the user can interact with in an easy way with these models and run simulations. For running simulations, some baseline input data are needed that are already known, let's say, by the system. But of course, the users should insert also their own inputs. And then after the simulation ends, they can simulate some outputs. So let's go to see what are these baseline inputs. The most important baseline inputs are, for example, the digital models of the terrain or the digital surface model at a high resolution, and they are very important to understand how water interacts with the land surface and the existing structures in case of flooding. So just to understand the difference between a digital terrain model and the digital surface model, as you can see in this picture, the digital terrain model is the one traced by this green line that shows the profile of the ground, of the bare soil, while the digital surface model takes into account all the elevation of the surface present, sorry, all the structures present on the soil, including trees. This is how such a model, a digital surface model, looks like. This is a digital surface model of the study area of Massa, which is one of the coastal cities included in involved in the SCORE project. And this is a map with a 2 meter by 2 meter spatial resolution. This means that this map is divided in cells that are squares of 2 meter by 2 meters, and every object that is, all the objects that are closer than 2 meters cannot be distinguished. So making a zoom on this area of the map, what we can see is this. As you can see, we can appreciate the profile of the terrain. Here we can see the bed of a river, but also we can see all these small rectangles that are the buildings. And this spatial resolution allows us to see many details. So it is a high enough resolution for our simulations. Another very important baseline input is a land use map that reports the land cover. These maps just tell us in each part of the study area what is the land cover. That is, if there is a farmland or abandoned farmland, if there are woods and shrubs, parks or public gardens, if there are streets or parkings. And it is also very important to understand how water interacts with the land surface, because depending on the land cover, the water arriving on the ground surface coming from a river or from a rain can change. Another very important baseline input is the riverbed geometries. That is a file that gives us the riverbed profile and the average water level in many points along the riverbed. And finally, one baseline, very important baseline input is represented by human and financial exposure and vulnerability maps. Here, this is a generic example of a exposure map of population, where we can see the different density of population in different area of the that is under analysis, and we can have similar maps that represent not the population living or working in the area, but also the buildings and the infrastructures and the associated economic value. Then, beyond the baseline input, we have the needed user inputs, because the users can set up simulations by ingesting some data related to the weather events they want to simulate. So they are asked to introduce some rain rates, some sea state, and some river discharge parameters. They can also simulate the implementation of ecosystem-based adaptation solutions. And this will be the topic of the presentation that will be done by my colleague Andrea Rucci. So finally, the user scenario evaluation module outputs consist in flooding maps and human financial risk maps on the study area. And we will see some practical examples at the end of this presentation. So I leave the floor to my colleague Andrea Rucci to continue the presentation.
So thank you, Giovanni. Thank you, Laura. My name is Andrea. I work in the Business Analytics and Optimization unit of MBI. And in the SCORE project, I work in the development of the digital twin and the early warning support system. In this part of the presentation, I will explain how EBAs are implemented in the digital twin, and then I will switch on the description of the early warning support submodule. So let's start. Just to recap what an EBA his. Other work packages worked on the definition of this ecosystem-based adaptation. These are interventions that we can do on the CCLL to face dangerous situation related to extreme events due to the climate change. In particular, they make use of biodiversity and ecosystem services. Here I have where we have an image of some of these interventions. In particular, we have 6 categories of EBAs. For example, the creation of urban green in the cities or the modification of the coastal shoreline. More in detail, there are 33 types of ABAs, and as Giovanni said, the role of the digital twin is also to allow user to simulate their effect. Here I have an example. In particular, on the website of the SCORE project, you can navigate and understand what are these ABAs. Here I have an example for the city of Sligo, in which there is, for example, a marram grass planting. That for each of them, one could understand the definition of the ABA, the scope, and the benefits of the intervention. But let's now analyze how we can integrate them in the digital twin. The idea is to allow the user to select an ABA and perform a kind of what-if analysis. So performance simulation, maybe using an historical event of the city, or also a new event on the city, and understand what are the effects of ABA in facing extreme events. You will see with the graphical user interface how the user can create the ABA. The steps are the following. One could select one of the ABAs, then define an area on the digital surface model. So define also some polygons on the map, and then apply an ABA. This ABA actually modify the baseline input with respect to the original one, and the user could also add some customization depending on the specific ABA. More in detail, since the digital twin has a hydraulic model inside, the ABA is actually characterized by essentially three variables. Once an ABA is selected, the modification of the input is done by modifying its Manning coefficient, that is a variable that describes the friction of the surface, the curve number, that is a number indicating the, let's say, the porosity of the terrain, and also the elevation of the ABA. These values are well known in the literature. For each land use, we know the values of this coefficient, so it's a good way to characterize an ABA to use these values. Now let's see more in detail all these three. The first one, as I said, the Manning coefficient, it is related to the roughness of a surface. So it enters the definition, the calculation of the speed of the water flow on a surface. So the resistance of the water to flow in a channel or in a floodplain. Let's say that in our inputs, we associate to each point of the digital surface model a value of the Manning. So the insertion of an ABA means that in the area defined by the user, we are modifying this coefficient. Here we have some values. For example, you will see there are different numbers for different land use, such as forest or river or sand, and so on. The second value is the so-called curve number. It is related to the infiltration of a surface. So in some way, it codes how how a part of terrain could absorb water till a certain level, and then allow the runoff over the terrain. Also, this value depends on the land use. Also, this value is associated to each point of the DSM, and then the application of an ABA is a modification or local modification of this value. The third one that is applied only to some of the ABAs is the modification of the elevation or shift. Here we have two examples of the ABA that could implement a modification of the elevation that are, for example, the deepening of a riverbed or the addition of sand on the beach on the coastline. What the user can modify the ABA and set what is the new elevation of the terrain, or, for example, to shift the original shape of the map. In this way, the hydraulic model could run on the new input data. So let's now switch to the early warning support. This is the second submodule that together with use define the digital twin. This module has a different scope. The use module was devoted to simulate different situations on the different kind of scenarios on the CCLL. With this module, instead, we want to implement a real-time monitoring of the current situation and understand if in short time there could be some dangerous situation. To do so, we start from essentially two kinds of inputs. The baseline input of the city, that is actually the same used for use, and also real-time data. Real-time data that is essentially sensor data, weather forecasts, and also in the context of score sensor from the population. Let's see how it works. The early warning support is essentially based on let's say, a library of scenarios that represent a list of possible events that could happen in the city. These could be events based on historical events or also newly created events. And for each scenario, we collected all the step of flooding, if the scenario concerns flooding, all the evolution of the time evolution of the events related to a scenario. So let's say, as an example, a scenario could be an historical event in which we had, for example, a certain rain event on the city, together with a certain event of the of a river, let's say a certain time evolution of its water level, and so on. These scenarios are created with the use, and then are related to the time evolution of the flooding of each event. Now, what we do is to run in background early warning support, collect real-time data, with high frequency, and perform a data preparation of this data. This data preparation concern, for example, the checking of the data from the sensor, so if there are missing data, outliers, and so on. With this data preparation step, we create what we call the current scenario. So is a scenario that represents the current situation of the city. Now that we have all the two ingredients, what we do is to feed a classificator that is based on artificial intelligence algorithm that has the role of associating a probability of each of the probability to each scenario in the library to the current situation. So we end up with a set of this set of probabilities. In this way, we can say, okay, in short, in some minutes, in the following hours, we could have a certain probability of a pattern of flooding if there is a danger. The last step is to decide, merge these probabilities with external data given by human and financial risk data that is prepared by another work package in the project. And then we make a decision. Let's say we do not select just the most probable scenario for the imminent future, but we interpolate this data also with the possible dangerous situation to decide what is the best advice to give to the user related to the imminent future. Then, if the scenario that we selected is related to a dangerous situation, through the graphical user interface, the user will notice an alert in the interface. We don't have also this alert, but we also implement what we call warnings that are related to problems in the real-time data. So as I said, we do a data preparation step in which we check if all the data is coherent, if there are strange data, if something is missing, and all this information are given through the graphical user interface to the user in order to let him know to actually check physically the sensor and all the sources. So as I said, baseline data required by the EWS is the same for the user, and it concerns so the digital surface model, the land use types, the information about the rivers, and also the exposure maps. Here we have an example of exposure maps that tells us the density of population, but there are also other exposure maps related to the streets, the roads, the value of the roads, buildings, and the railways. The other input is the real-time data. As I said, we currently could monitor rain rate, river level, and for example the sea state. From official sensor, we read also data for weather forecasts to allow to select to allow a better selection of the current scenario. And also in the SCORE project, we use citizen science sensors. The output of the early warning, as I said, is made up of alerts. So if the early warning support module decide that there could be a dangerous situation, the user would notice an alert in the interface, also warnings related to specific sensors. But in the case of an alert, the output will be also in the output, there will be also a map of the expected flooding in the imminent future, and also the danger computed from the risk maps using the vulnerability function given by other work packages in the project. And so I finished this part. I think I can give the word to Jose.
Good morning, everyone. I'm Jose from UCD, from the Spatial Dynamics Lab, and I'm working on the development of digital tools for stakeholder engagement and citizen science activities. So I'm collaborating with the MBI group in the user interface that I'm going to do a quick demo, let's say, about the user interface for the digital twin. So let me start sharing my my screen. Give me a minute.
Yes,
Now
we can see
you can
it.
see. Perfect. So the digital twin user interface is going to be in some point the final version deployed online to be accessed by the CCLLs. So now I'm showing the testing version that we have in this moment, and for the Masa user. Here you arrive into the main map where some of the layers, well, the baseline layers can be found, and also the results from the simulations and from the early warning support system will be showing here. But I want to start first with the user scenario evaluation that was presented first by Giovanni and Andrea. Here you can see some of scenarios that we have previous, but let's go through the user from the CCLL can create any new scenario, having some description. I prepare some text to go quickly. The most important here is to name the scenario with a name that represents what the people want to do, the CCL want to do, then the scenario description. And then another important thing is setting up the duration in minutes of the scenario. Let's start with 60 minutes. So after that, we can enter the configuration of the scenario where the user can start creating some ABI solutions, but also entering the simulation parameters to run the simulation. For example, let's start with the ABI. The ABI for this scenario and for Masa, we have different options from the catalog that Andrea showed before. And the user should select one of them. For example, do restoration, create the description of what the user wants to do with this ABI type. And then the user can start mapping the area where wants to implement the ABI solution. For example, if we can change to the satellite image and then digitizing some of the polygons of the ABA. Also, we can modify the digital terrain model with entering. In this case, we are entering a delta variation of the meters of the elevation. Let's say is a relative change in this case to the area. For example, with the changes, we will have a 2 meters elevation delta, so the user can start creating another polygons, let's say here, entering the different variation in the terrain model, and then saving the ABA. So here we have our first ABA, and well, the user can enter any ABAs that he wants. Let's, for the purpose of today, let's go with one. Then the second part would be the addition of the different parameters. This area, the user can enter the information related to the sea state, to the river flows, when one or more rivers are in the area, and in relation to the rainfall rates. For example, let's start with the sea state. Here, we can we have two options: the manual input and some of the predefined long-term scenarios. The same thing applies for the river flows, for the manual input or the predefined long-term scenarios. So let me start with the sea state, having some range times with the value, a sea level of 2 meters. Here, a table start to collect the data the user is entering. Let's go with another to finish. We need 10 minutes more. And in that sense, let's put sea level data. and we finish with the 60 minutes of the simulation, of the duration of the simulation. So after that, we can save the data. We can go into river flows. Let's say if in the river flows we want to start with a predefined long-term scenario, maybe a future scenario, selecting the risk, the time span, the return time 25 years, and then we set up the long-term scenario for this case. And finally, if we go into the different rainfall rate, we can start with 20 millimeters per hour, then enter another change, let's say 40, let's say, sorry, 5, and finally, to complete the 60 minutes duration of the simulation, we go with 20 and save the different values. So after all the data is complete, for each of the parameters, we have, and all the ADVs are entered. We have the complete. Let's start with another one very quickly. Just to see the different ABIs on the map before running the simulations. Here we can have the previous one. This one was the dune restoration that we did before. And let's start with the second ABI type. Oops, sorry about it. The green corridors. Let's go here. Let's try something like this. Difference of 10 meters in this case. So after saving it, we can go into the main map. For example, in this case, we have the different types of ABI. We have the dune restoration, the green corridors that should be in somewhere. Okay, is here. We can change the different base maps. For example, this one is the corridor ABI that we created. These ones are the polygons for the dune restoration. Also here, as I said before, we have some base data from the zip. For example, let's load the rivers, and also we can have 2D and 3D views. My internet, I suppose, is a little bit slow, but well, you're seeing here the different rivers that we have as baseline data. So after you have all the ABAs and the parameters entered, you can actually run the simulation. And this one is our referential. So the simulation started, we created at this point, and well, is in progress. So after the simulation is end, we will have a human readable report with summarizing all the data, all the parameters that we entered into the scenario when we were setting up. We also will have the detailed maps, geomaps, linked to see on the main map visualization with other layers as a contextual reference, and also we will have the results in this human report that will be based on PDF. And for example, if we go into well, Giovanni is going to show more about the results, but for example, this is a result coming from the early warning support system that is very similar to the simulation results. Well, finally, to conclude, I want to show you the different management of the sensors from the early warning support system that the users that can manage and pick which sensors want to be enabled and disabled when running the early warning support system automatically. For example, here we have a sensor that is not enabled. The sensor has different data streams coming from the ZIPs, from the Sensor Fix API, and we can see the different warnings coming from the digital twin API prepared by MBI. when we have warnings, we can find it here for the users. Also, we can see observations, the past observations to see how the sensor is working, and enable the disable. For example, this one is enabled. The user can, for example, disable here. Now we can, yeah, now is disabled. See any warnings and see the observation. So the user that has control over the early warning support system can manage and see the different warnings that also in this case the early warning support status is green, so all is okay. But when we are having a problem with some of the data stream that actually are used by the simulations, well, the icon of the sensor will change into yellow, and also the status of the overall system will be changing. So in this area is for having the control about the different sensors that the early warning is using. In the case of the users that are not managing the early warning support system, also some data from the SIP, for example, the same sensors can be loaded for other data, but without manipulating them to disable or to enable. Well, I think it's a little bit slow. Now it's here. For example, we have this one, and with other values. So I suppose I'm going to stop sharing and give the floor to Giovanni to tell us more about the results, the simulation results. Thank you so much.
Okay, thank you. So let's go to see some examples of simulation outputs. Here I report the example of a simulation where there is a GIF that is composed by 20 frames showing the evolution of water on the ground during a simulation. These are, let's say, outputs at different time of a simulation of a duration of 1 hour, with event settings set as 15 minutes of no rain, 30 minutes of 200 millimeter per hour of rain, which is a quite intense precipitation, and 15 minutes no rain. So what you can see here is the map of Massa that I showed you before, and you just see, as the time goes by, you see the where it colors in blue is where water remains, water accumulates, and the system is able to produce maps where the users can see the level of water in each cell, 2 meter by 2 meter cell of the map. So if we make a zoom of these maps, what we can see is this. This is an output that both the early warning support system and the use scenario evaluation subsystem can give. The early warning support subsystem will give this such an output in case of an alert, while the user scenario evaluation system will do it at the output of a simulation launched by a user. So at the end of the simulation, what we can see is a map of the city with the areas covered by water, and there also the water level can be measured. This is just a first result that to be better understood must be overlaid with other inputs of the system. In particular, we have to understand how this flood can affect population. So the way that the system proceeds is overlaying the exposed population map with the flooding map. So we can see in each cell how many people are affected by flooding. Here you can see in this small yellow square the number of people that live or works in these areas. Something similar can be done not using the maps related to population, but related to buildings, to the value of buildings. And in the same way, we can the system can calculate the economic damage in each cell of the map, depending on the water level and on the economic value or the use of the buildings. So in each cell, as it can be seen in this yellow square here, the damage in euros to the buildings is reported. Again, the same thing can be performed on infrastructures. In this case, infrastructure are considered the roads and the railways. All these data have been provided, as Andrea said, by our partners in work package 6 in the SCORE project. And here again, we can see for each piece of infrastructure the damage that has been caused by flooding. It depends not only on the value of the affected infrastructure, but also on the water level in that cells of the map. So to conclude this presentation, we have seen that digital twins are a powerful tool to safely analyze real-world systems and processes without the need of directly interact with them. In the SCORE project, we developed a digital twin early warning support system that is intended to support coastal cities in enhancing their resilience against climate change. This system is composed by several modules, and the most important one from a functional point of view are the use module that is used for simulations that users can employ to run simulations about weather event and possible countermeasures that can be implemented, and the early warning support module that launch alerts in case of imminent flooding. This system, as we showed, is equipped with a GUI that helps users intuitively operate with it, because usually the hydraulic models or the physical models that are employed for this kind of simulations are used by people that are experts, that are they work with the models in this field. So we try to give users an easy way, user-friendly way to use this tool. Then users can also predict the impact of the ecosystem-based adaptation solutions on improving the resilience of their cities against climate change, which is one of the main aims of the SCORE project. And the output maps of this system contain the flooding levels and the damages to people, buildings, infrastructure, helping in long as well in the short-term disaster prevention. In the long term, because thanks to the user scenario evaluation simulations, people can plan the land use of their urban areas. And but also thanks to the early warning support subsystem, disaster prevention can be managed also in emergencies in case of imminent floods. The presented system here is very flexible, and since it is a software framework that can adopt different physical models, not only hydraulic models, but also climate, surface land climate models, or air quality models, they can be adapted to other use cases other than coastal cities. I'm here to answer to any question. Thank you for your attention.
Thank you very much, Giovanni, and all, Andrea and Jose. We have not received any question in the chat, but I don't know if we will have any in the next minutes. Otherwise, maybe people will have some questions in the next days or weeks. In this case, you can always contact us by email.
Yeah, sure.
And also we have a section on the website where we have deliverables, and you can also access some of the deliverables related to the digital twin, which is under work package 8. I put the link here in the chat. And I can see there is a hand raised. So I allow the mic if yeah, you should be able to speak. Raimundo.
Hi, Giovanni. Good morning.
Hello, Raimundo.
Well, first of all, congratulations for the presentation. It was very descriptive and really good content. So
Thank you very much.
I was wondering about the running time of the scenarios. If you already tested any bunch or of any group of the scenario that Jose Pablo was describing, and I was wondering about what's the real time I know that it depends the amount of scenario, the detail, the extension, but the computing time for an average, what could you say about it?
For the moment, thank you for this question. It is a very important point. For the moment, we ran some tests on the city of Massa, which is our pilot case. And for the area, for the study area that has been considered, that is some kilometers squared with a 2 meter by 2 meter resolution. For the moment, we could find the way to optimize the simulation times, and now we can simulate, for example, 1 hour in few minutes. By memory, I think I remember 6 minutes for a 1 hour simulation. For the as regards and it needs, of course, the higher the level of detail of the maps, and the higher will be the computational time. We think that 2 meter by 2 meter or even 4 meter by 4 meter resolution of the maps can be a good trade-off, let's say, between the level of detail and the running time of the simulations. As regards the early warning support system in particular, it is faster. It is much faster because it does not run every time the hydraulic models as the user module does. Since thanks to, let's say, its training and to the artificial intelligence algorithm, it can give let's say at a glance evaluate the situation and make one of the scenarios he already knows correspond to the current situation, and it gives an output every 15 minutes.
Okay, that's a very good computational time for even an application of a real or semi-real monitoring time. It could, from my point of view, it could be a high potential to adaptate this kind of software for a real-time monitoring and not only early warning system.
Thank you.
Laura, you are muted.
Okay, sorry. We have another question. I opened the mic of Albert Indiana. We cannot hear you.
Sorry, can you hear me now?
Yes.
Yes.
Oh, yeah, great. Yeah, thank you very much for the presentation, Giovanni. I really enjoyed it. So I just have a quick question in relation to early warning system. So how many simulation had you done for your hydraulic model, so you have some certainty in regards to your foreseen for for the new set of conditions of extremes. Yeah.
Okay, I will leave my colleague Andrea answer to that question, because he's the one that is developing in particular this submodule of the system.
Mm-hmm.
Right. Thank you for the question. Is actually the crucial point of the early warning support. Now we are working now on Massa to create the scenarios of the library. We think that order of 10 or 20 scenarios could be enough to represent the current situation, but this is just a starting point, meaning that we are now facing starting and faces the validation phase of the system, and in this validation phase we will see what are the details about the creation of the library. The important point is that each scenario is not related to the probability of happening of its historical probability. This is, I think, the important factor related to these scenarios. And sure, the more the scenarios, the more detailed the scenarios, the better will be the classification task. But during the validation phase, we will see if this first idea based on our test on Massa of 10, 12, 10 or 20 scenarios could be good enough, or we could also add scenarios in the way.
Mm-hmm.
Let me add finally that these scenarios are not fixed. Meaning that one could also add scenarios during the when the early warning support is working. So one could also add new scenarios and create a better classification.
Yeah, that's great. Yeah, and that's a fair approach. How are you doing it? We're doing similar things at the University of Galway, not through digital twin, but we do have a good hydrodynamic model and a lot of statistical analysis to understand all the extremes and how we can use this extreme value analysis to force the model and make a prediction of a flat. So thanks very much. Very interesting, guys. Yeah, well done.
Thank you.
Laura, I see you're muted. I see a question in the chat.
Yes.
We have
Wagner Costa asking for more information about citizen science sensors. How do they work and what are they? So this will require a lot of time, but maybe just
another webinar. So just I can just
we did another webinar on this. I put the link in the chat here, but you can maybe give just a brief answer for the moment, and then
yes. The short answer is that each coastal city involved in the project will choose its own. They have a budget to buy some citizen science sensors. Of course, each city maybe will be more interested in some parameters, so each one will choose its own. In the case of Massa, they bought some hydrometers, some cameras to monitor rivers, and some smart LNBs that are devices that are usually used for satellite internet connection that are provided by MBI, but they can be used also as rain rate sensors, thanks to specific algorithms that have been developed by MBI and the University of Pisa in other projects. So our aim is to include in the sensor networks that will be employed by the early warning support system also the citizen science sensors, because at the moment we are just relying on official sensors. Tuscany region agency, but we hope we can find the way to properly calibrate the citizen science sensors and integrate them in the network that will be employed by the early warning support system.
Perfect, thank you. So you'll find the link in the chat of the webinar we organize on that. Any other questions? Otherwise, it's already 12 o'clock. So I also remind you that the recording of this webinar will also be made available on the SCORE YouTube channel next week. And yes, you'll find also in the chat the feedback questionnaire that to provide feedback on this webinar. You can fill it. Thank you very much. So
Thanks very
thank you
much.
again to all the speakers. It was very interesting.
Thank you.